Hey guys, today we'll be talking about conjugated dienes and why these systems are so important in our next chapter in organic chemistry. So far, we've already talked about a double bond on a straight chain, but only one double bond. But now we'll be looking at two double bonds and how this is a different system. So when we have two double bonds that are separated by one single bond, as we were about to talk about, this is called a conjugated system. We're going to talk a little bit more about why these are so special and how to add to these conjugated dienes, as we've only added to a single double bond on a straight chain. So in this system I have right here, you can see that we have two double bonds that are separated by a single bond right in the middle. And that is only one single bond separating these two double bonds that we have. This is so important because it affects the stability of our molecule in a different way than what we have been looking at in the past. To my right, to the molecule that we have just talked about, I have drawn a benzene, which is a very famous conjugated system that we probably didn't know was a conjugated system in the past. And as I said before, and as we should know now, a conjugated system is where we have our double bonds, each separated by a single bond right in between them. All right, guys, so I found this energy diagram online and I find it very helpful to what we're learning and why it's so important and what it has to do with the additions that we are about to make to this conjugated system. So we've previously dealt with isolated systems and additions to those systems and what those additions look like. And now that we're dealing with conjugated systems, we need to know how those are different than those isolated systems. So this chart here shows us that as we have a conjugated system added into our molecule, the energy actually goes down. And what does that mean for us? If we think back to general chemistry, we'll remember that a lower energy molecule actually means a more stable molecule overall. And that is so important for us because that produces a different type of addition when we come to add to these conjugated dienes. That also tells us why benzene is such an important molecule in organic chemistry, because it is the most stable molecule that we will be dealing with in this unit. All right, guys, on to the last part of this lesson, addition to conjugated dienes. So as I said before, there are only two ways to add to a conjugated diene, and that is either at the 1 and 2 position or the 1 and 4 position. So this molecule we're looking at right here is a 1,3-butadiene. And what does that mean? Well, we have a 4-carbon chain, which is where buta comes from. And then we have a double bond starting at carbon 1 and a double bond starting at carbon 3. We have that single bond right in there in between carbons 2 and 3. So we know we have a conjugated system that we are looking at. So the two ways that we can add to this conjugated diene are either at the 1 and 2 position or the 1 and 4 position. The 1 and 2 position will always give us our kinetic product, but the 1 and 4 position, we don't know whether it will give us a thermodynamic product or not. The thermodynamic product depends on what the double bond looks like at that position. All right, so we'll be specifically looking at our kinetic product in this example, which we said was a 1-2 addition always. And one thing to remember for both our kinetic and thermodynamic products, the 1 position will always be taken up by our hydrogen in our solution, and either at the 2 or 4 position we will be adding whatever else we have in our solution. So right here you see that hydrogen is adding to that 1 position, and we have a carbocation forming at the 2 position because we are looking at the kinetic product. And this kinetic product is important because it's the low temperature product, which means that at low temperatures, our molecule is forming whatever is easiest for it to form, and that is where our double bond is lost between carbons 1 and 2, and we form a carbocation at carbon 2, and our bromine attaches at position 2. Now that we've talked about our kinetic product and how that will always be the 1-2 addition, we will be talking about the 1-4 addition to conjugated dienes and how that is not always our thermodynamic product. Our thermodynamic product may be the 1-4 addition, but it can also be the 1-2 addition. And that is because our thermodynamic product depends on the double bond that we are forming, and we want to form the most stable double bond in our solution. Our thermodynamic product happens at higher temperatures, and that gives our molecule more time to decide where it wants to add and what kind of stability it wants to have. whereas our kinetic product is happening at low temperatures, so it will form whatever is fastest for it. In the 1,4 addition, we are again adding hydrogen at the 1 position, but what is different is bromine adds to the 4 position, and we have our double bond moving to the middle. And that is because we are actually using a resonance contributor. So we add our hydrogen to the 1 position. Hydrogen is reached out to by that double bond. Bromine falls off. We have our carbocation forming, and then we have our resonance contributor forming, and that is what is actually being used to form the 1,4 addition. Bromine attaches to the 4 position, and we have a new molecule forming with a double bond between positions 2 and 3. All right, so I want you guys to look at this example that I drew out for you all and determine what our products will be given the 2 conditions we have. So we have negative 40 degrees Celsius and we have positive 70 degrees Celsius. What do those 2 things mean to you all in relation to the kinetic and thermodynamic products that we were talking about? If you said that the negative 40 degrees Celsius would yield our kinetic product, that would be correct, which means that we were adding 2 carbons 1 and 2 of our conjugated diene. We have hydrogen at carbon 1, bromine at carbon 2, and our double bond between 3 and 4. So that 70 degrees Celsius tells us that we want the thermodynamic product because it is a much higher temperature. So we're going to draw out both the 1,2 addition and the 1,4 addition. And we're going to determine which one is the thermodynamic product depending on which one yields a more stable double bond or a more substituted double bond. If we take a look at the one on the left, we have our double bond surrounded by 3 hydrogen groups and 1 carbon group. And the one on the right has 1 hydrogen group attached to it and 3 other carbon groups that I highlighted in blue. So we can say that the one on the right is by far the most substituted, most stable double bond. So in this circumstance, our 1,4 addition was our thermodynamic product. Hope this all made sense to y'all, and have a good rest of your day.